Like I'm trying to get up.
Basically, and also the ground. I have like a 90%, right?
What are you doing? If you want to
Yeah, don't look like a 90%.
I'm distributing, but I what time do you get back? What time do you like start over?
It's like that's just like.
All right,
I'd have been like solid 10 seconds.
let me go over one of the homework problems here. So this is number 11. Off of the AP review. I think, yeah, I didn't get a chance to fully work out the problem on the key, so just wanted to make sure you guys saw this here. It says, what is an equation of the tangent line to the graph of the function at the point where f prime is equal to 2? So we're looking for a tangent line equation. So ultimately, we're trying to find an order pair and slope. Well, the slope is already given to us, so that's nice. F prime equals 2. We just have to find the order pair. So maybe the graph looks something like this, right? And we know the slope is 2. We just have to figure out what is the slope of that tangent line, or what is the equation of that tangent line. So what we can do is we only have we have information about the curve. We know what the slope is, but we don't know where that exact point is. So what we can do is we can work with that f prime, right? If we set f prime to equal to f prime of x, we can kind of get the informations to line up, and that way, if we know what the slope is from the derivative, we can work backwards and solve for x. So solve for x, I can bring everything over to one side, set equal to 0, factor out the 2. And this is a calculator question here. What I can do is I can enter that into the calculator and look for the intersection with the x-intercept. So if I sketch that graph and identify the x-intercept of this equation, it ends up being 0.3129. So we know that this x value is 0.3129. We know what the slope is. We just have to figure out what the y value is. Well, we know what the equation is. We can insert that 0.3129 back into the original function to get the y value. And once we get the y value, then we do point slope form, and we just solve for y to the point that we can match with the answer choice. So I think I only worked this halfway out on the key, and I didn't finish it. So.
Trick for number 7 instead of like, because I just plugged in x values.
Yeah. I mean, we could split it up into piecewise functions and look for the derivative, but it's easiest to just sketch that graph out.
Just by looking at.
Yeah, just by looking at the graph, right? You know that the absolute value function has a vertex at 4, 1, and it's pointing up. So you know what the graph looks like, and you know that our function is never differentiable. The slope is never going to exist at a sharp turn. So it's just by looking at the graph, that's the fastest way to get to our answer. Okay, so let's look at today's topic, product and quotient rule. Page 9 in your packet. Now, we talked about how one of the conditions for power rule is we have to resolve all the exponents, right? We have to get all the parentheses to go away, everything expanded out before we can do power rule. But now we're being introduced to not only polynomials that uses power rule, we've also been exposed to exponential function, log functions, trig functions. And if I want to find the derivative, that involves
two different types of functions where I cannot resolve it into one expression, then I have to go through something called product rule. So product rule is where I have no way around two different functions being paired together. And it's not quite the same thing as just finding the derivative of one term and multiply with the derivative of the other term. I mean, it works if it's h of x equals f plus g, then that's fine. If it's separated by plus or minus, each term can get their own derivative treatment, and we can just merge them together and there's no issues. But anytime we introduce multiplication into it, we do involve both terms derivative, but it's a little bit more than just that. Okay, so here's the rule that we're going to do. We're going to whatever you can name, whichever function is f, whichever is g. For me, whatever shows up first, I'm gonna assign it f, and whatever shows up second, I'm going to call it g. So if I want to find the full derivative of the product of two terms, it's f prime times g plus f times g prime. So we're basically having each term pair with a derivative of the other, and vice versa. So we take the derivative of the first, multiply by the original second, plus the original of the first times the derivative of the second. So let's give number one a try here. F of x equals 8x sine x. These are obviously the product of two terms. I cannot merge it into one because these are different families of functions. So I know I got to go through product rule. If I do want to find the derivative, I'm going to assign 8x to be my f, and I'll assign sine x to be my g. Okay, so this is what I need to have in place if I want to find the full derivative. F prime, what's the derivative of 8x? Okay, the original g function, no changes. Back to f. And then g prime, what's sine x's derivative? Cosine x. So this is as far as we can go. Not much we can do beyond that in terms of cleanup. Okay, number two, g of x is 2e to the x times square root of x. This one I can use exponential rule, and this one I can use power rule. But for power rule, I can rewrite this as x to the 1/2, right, to get it ready for power rule. And obviously these cannot merge into one term. These are, I have to leave them separate the way that they are. What's the rule for e to the x? Just e to the x. That's nice, right? The derivative of e to the x is simply just e to the x. So go ahead and set up what you want to find for each part of your product rule. And then we'll compare our answers. And then from there, I just try to clean this up a little bit. I don't want any negative exponents in my final answer, so I brought that x down. You can leave that denominator as x to the 1/2, or rewrite as square root of x, just want to give some options. You don't have to have radical, you can have it as a rational exponent, just no negative exponent, yeah. We could, yeah, so I'm not gonna require that we end up having to factor unless we're looking for critical points or things like that, but right now, yeah, unsimplified or unfactored is completely fine. All right, sometimes, okay, any questions with two? So sometimes you do have a choice. Sometimes you don't have to use product rule if it's possible for you to expand. So for instance, number 3, this is perfectly acceptable if you want to just FOIL everything out because those terms are within the same family where you can expand everything out, get everything ready for power rule and apply power rule, and that works. But let's just for practice purposes, let's see if we can just go through product rule for number 3 as well. Okay. But we do need to kind of get that first term ready for power rule by bringing that x up to the top. Yeah, so just want to show you how far we could go in terms of cleanup here. So I am going to distribute the the variables through the parentheses, and I'm actually able to kind of separate into individual terms. I think this is good practice for us. Obviously, if it was true response, any of these variations are fine, but I just want us to kind of get that practice with, you know, combining and going as far and cleaning up as far as you can go. Again, if there's only one term in the denominator of your fraction, you're more than, you have that ability to split up into individual pieces. Okay, any questions with 3? And as messy as this process is, the end result is simply the derivative function. Again, the derivative function, all it does is serve the same purpose as other derivatives. It just describes the slope behavior of the original function. So, you know, we're going to learn all these different derivative rules, but the end result is just giving us the same thing as other derivative functions to serve the same purpose.
Can I just leave it like the second step there?
I don't want negative exponents, so you have to go to some variation of that third step.
Okay.
Yeah. Okay, are we good with 3? Then move on. All right, so here's number 4. Now, sometimes we may have to do product rule of something that is in function notation. If that's the case, then just find the derivative in function notation. So for instance, here we have a table that shows 2 differentiable functions. That just means we have 2 functions that's smooth curve. There's no sharp turns anywhere. F and G are the 2 functions, and here are some specific values that's given to us. H is defined as 3 f of x g of x, find h prime of 2. This is a 2-step process. We have to find h prime of x before we can find h prime of 2. So we can tell that the relationship between f and g is a multiplication relationship. So because of that, if I want to find the derivative, I have to go through product rule. So I'm going to go ahead and just assign my f and g. My f is that 3 times f of x. Anytime there's a number attached to a variable, just think of that as a coefficient. It's just going to tag along to whatever the derivative is. It's not a constant. It's not a constant in terms of that it's by itself. That 3 will just tag along to whatever you find as a derivative. Okay, so we have to go through product rule here. So I'm going to kind of spell out my steps here. All right, so what's the derivative of f of x? F prime, yeah, so if it's function notation, we have to leave it in function notation. The 3 will tag along with it, so it'll be 3 f prime of x times, no changes, we just want the original g function. Back to f, no changes, just want the original f. G prime, we just want the derivative of this term here, so now that we have our derivative function built, we can take the next step and find h prime of 2. We want to find the slope of the h graph at 2, replace every x with 2, and then you can get it out of function notation and have that exact value.
So on the test, you'll take any simplified or non-simplified version of the answer. What about the AP test?
AP test, chances are, if you see a problem like this, actually,
That one, the ones above.
oh, the ones above. Chances are, if you see a problem from ones above, yeah, any variation they'll accept. But typically, derivative problems show up on multiple choice.
Oh, yeah.
Yeah,
Okay.
so, but if it's free response, yeah, they'll be very flexible in terms of what they'll accept.
More multiple.
Yeah, more multiple choice than free response, yeah. Oh, so we've built our derivative function with the first step, but it's asking for h prime of 2. So to find h prime of 2, I'm going to replace every x I see with 2 for x. And then once I find that, then I'm just using my table of values to get it out of function notation. So f prime of 2 is just going to be -2. And then g of 2 is just going to be -1. F of 2 is 4, and g prime of 2 is 2. Okay. Questions with 4? Now take a look at number 5. Number 5, there is a mix between function notation and numeric values. So we may have to take each derivative appropriately. So I'm just going to assign my first term as my f as the f of x over 2 plus 2. Anytime I see a fractional value, I like to pull it in front as as a, or if I see a denominator, I like to pull it out as a coefficient and a fractional value. It just feels a little bit cleaner looking at a number in front rather than a number below the variable. So I feel like 1/2 f of x feels a little bit cleaner to work with than f of x over 2. And then, so I'm going to assign the first parentheses as the f and the second parentheses as my g. So let me just kind of go through this here. What do you think the derivative of f would be, of this would be? 1/2 f prime, and the 2 would go to 0. Good. What's the derivative of 3 minus g of x? Negative g prime. The 3 would go to 0. Okay, so you would set up each of the parts of your product rule. And then once you have your derivative built, then replace all the x's with -5, and then use the table to convert the remaining function terms and function notation into numeric values and then merge them all together.
So I mean, like that.
Thanks. Okay, any questions with 5? I'm going to leave the bottom half just for practice later, but I think we get that understanding, right? That anytime things are merged together or multiplied together, unless we can merge them into the same term, we're going to have to rely on product rule to get through the derivative. Yeah.
Would it be -5 times 2?
Oh, this part right here?
G prime or -5. And -5, oh, yeah, so it's just 2 times 5, right? 2 times 5. Any other questions here? Okay, so let's go to the next page and let me introduce the other variation relationship between two terms is what if they're numerator and denominator relationship there. So if I want to find the derivative of a numerator over a denominator, we do involve both terms derivatives, but because they're divided by each other, it's not as clean as just subtracting or adding between two terms. So we have a special rule, quotient rule here. If I have a numerator over denominator, if I want to find the derivative of the individual of the full expression there, it's going to be f prime times g. So very similar relationship initially, but the next is going to be minus fg prime. So we still have that f prime g and fg prime, but instead of plus is minus, and there's also a denominator portion divided by g squared, the original g function squared. Okay, so number one here, I have 2x squared over 3x plus 1. These are numerator and denominator relationship here. So if I want to find the full derivative, I'll call the numerator f, I'll call the denominator g. I'm going to find y prime. Okay, so f prime for x, the original g function, back to f, g prime, all over my full denominator squared. And for now, I just want us to practice cleaning up all the way. I think that will be good for later on when we're having to do critical points and further down the line. But leaving your answer unsimplified is okay, but just for practice purposes, let's see how far we can get to clean up all the way. And even with this, there are different variations of this. You can factor in x if you wanted to, but this is pretty clean already. And anytime something is already in factored form, we usually want to leave that in this form. Factored form is going to be the most useful form down the line when we're having to look for different things like curve sketching and properties of the graph. Right. Try number 2. For number 1.
Wait a minute, never mind, I just forgot.
Okay. Make sure when you square your denominator that you're putting parentheses around the denominator first before squaring it. So just be careful that you don't put 2x squared instead of 4x squared, right? Your whole denominator is getting squared, so the 2 is also seeing the exponent, not just the x. Okay, any questions with 1 or 2? Now, I do want to point out something about quotient rule here, and I want to look at number 4 for a second. Number 4. Obviously, we can do quotient rule, okay, numerator denominator, but is there another way to look at this problem? Right. There's something about this problem that allows us to have a different path that we couldn't do before. The denominator has only what? 1 term. Now, I know we have only one term for number 2, but these are not in the same family of functions. We're not able to merge it. But just be aware that if there's only 1 term in the denominator, there is that option. Doesn't mean that you can choose, but I want to give you an option because there are times when splitting up is preferable in terms of reaching your answer faster than having to go through quotient. Because quotient rule is a little bit of a last resort. I mean, it works, but it's just there's a lot of pieces and parts to clean up, right? And sometimes if you can just split up into individual fractions and being able to avoid quotient rule, you can arrive at your answer faster using power rule. Okay, and just want to kind of give you that option. Obviously, if you chose to do this quotient rule, you could. It just takes a little bit longer. And on the AP exam, the more efficient you can be, the more you can save your time for other things. So in this case, let's say I want to go through a power rule here, right? So I would clean this up. I would make this 3/2 x to the -1 plus 1/2 x to the -2. So now I'm able to split up into individual pieces. And I can just go through power rule once I have the full separation between these 2 terms. You'll get the same thing using quotient rule. It's just, I guess in this case, it's not that much of a difference because this is not too complicated going through quotient rule. But if you look down at the rest of this page, do you see another place that we could avoid quotient rule? Where else on the sheet can we avoid quotient rule? Yeah, if you look at number 3 there. So, and this is a good one where, anytime you see a denominator, I think it's good to 1 term. It's always good to split up. It can save some time, especially if we can avoid quotient rule. But you can only do that. There's only 1 term, right? We can't do that. As soon as there's more than 1 term in the denominator, we're forced into quotient rule. But the problem like number 3, the derivative is going to be a lot faster, a lot cleaner, splitting up, just doing power rule for each term. Okay, last one here. Can we do number 5? Number 5, we will do quotient rule here, but we would take turns with each derivative. We build h prime first, and then we can plug 2 into the derivative. Okay, there's a few more variations of product and quotient rule that I want to explore on the third and fourth page of this packet. So we'll do that tomorrow. And then 2.5 derivatives of other trig functions should go fast. That should be easy. And then we can start doing our test review on, quiz review on Friday, and then quiz review Monday. But I'm going to jump into chain rule, the next section, 3.1, which is not on your quiz, but give you a day extra to review for your quiz. All right, come get your phones. You guys have homework tonight from 2.4, product quotient rule, so check your calendar.
I know some people. Working on it.
I used to have a.
Keep it there, yeah.
It's like, well,
For instance, this one where it's plus one.
Yeah, but then it goes away.
But I never went to sales action monuments.
I mean, that's just the.
Like when you just.
The thing is,
I just imagine. Yeah. Actually got it. So much fun.
Can I show you our HEG?
Make a big deal out of it. Make it get bad.
Yeah.
That's not like my. I think. I could
And it's. I know.
have. So like, right, maybe if they see that here.
Yeah.
Was it done?